Continuous continuum. Right from there. Come on. Cross credit. Okay. Cross credit. The resolution of it.
You can change the slide from here and you need to do that mouse setting you have. You're pointing and you then you need to increase from your mouse
Pointer
pointing.
option. If I make it laser pointer, then what
Yes.
happens?
Then it's maybe. Okay.
Now nothing is on this will now, no?
This one.
Okay, excellent. Why is that arrow there?
I will. Because it's here.
Oh, okay.
Now you check with the pointer. So that
It's kind of slow, but
okay, I'll bring it as a pointer.
why is something?
No, अभी नहीं चलेगा नहीं चलेगा.
Oh, अच्छा. Okay.
हो गया?
हाँ, ठीक है.
बढ़िया.
मैं वॉशरूम होके आती हूँ.
हाँ, बिल्कुल, ये.
हाँ.
इनको ज्वाइन करने दीजिए माइक्राई को ज्वाइन करने दीजिए माइक्राई को हाँ हाँ उनको आचार्य को भी जाने दीजिए अगर अलग रे ज्वाइन करें ना अलग रे अगर ज्वाइन करें देखो क्या है
Hello, Professor Acharya. How are you?
Yeah, I am fine. Yes, thank you.
Good to see you. Good to see you.
Yeah.
अरे सामने आके बैठे हो भाई क्या हो खाली है पीछे बैठे हो और सामने आके बैठे अरे नहीं आ जाओ अरे सीखो इधर मुझे बहुत दूर फ्रिक्शन डिसिपेशन की तरह लगेगा अब तो पहचान लिया है बैठ जाओ चलो उधर से इधर आके देखना पड़ता है ना वैसे में पहचान लिया अब आप दूर से लाए नहीं अभी तक तो कोई आया ही नहीं हाँ
लाइव स्ट्रीम चालू कर दिया
लाइव स्ट्रीम चालू कर दिया हाँ चलो आप बैठो
हाँ
कोई इशू नहीं है
Sure,
एंड ये थोड़ा पहनना पड़ेगा आपको
हाँ हाँ
और you want to fix it?
मेरे दिमाग में अभी भी चल रहा है एक स्लाइड और ऐड कर देते हैं
ऐसा क्या?
इट्स एक्चुअली टू बी ऑनेस्ट मुझे लग रहा था कि इतने सारे स्लाइड की जरूरत नहीं है पर अब लग रहा है कि हाँ एक स्लाइड और ऐड कर देते हैं कि इसके अलावा भी मैं ये सब भी करती हूँ तो मैं अब ऐसे ही इन वर्ड्स बोल दूंगी कि हाँ मैं ये सब भी और करती हूँ जिसके बारे में आप नहीं सुनोगे बट as someone says like picture is 1,000 words and a video is a million words so
Hi, Shreyash. Miss Prerna. Shreyash.
I
चलो। हाँ बट मुझको भी नहीं लगा। तो यहाँ से अटेंड कर सकते हैं उनको हम एंटर नहीं करने देंगे जूम में हाँ इसमें क्या हुआ था कि सब लोग कोई यहाँ पे नहीं अटेंड कर रहा था जूम के थ्रू अटेंड कर रहा था
गौतम तो यही बोल के गए हैं कि
क्या
he is here but वो जूम के थ्रू आना चाहते हैं टाइप्स
पर वो अलाउड नहीं है गौतम को ही पता होना चाहिए
तो मैत्री भी लॉग इन किए हैं
मैत्रेयी तो ठीक है मैत्रेयी
Hi, Prerna. Sorry, I keep missing you even when I see you in person. So we'll catch up.
yeah
Catch up.
yes I'm coming back to Bangalore we can meet there tonight itself
2 जन कौन है 2 जन कौन है एक्स्ट्रा कवर और नहीं जानता नहीं नहीं अलाउड नहीं वो तो निकल गया अच्छे से ठीक ना
How is your son? Is he okay?
No, yeah, he's in.
Good, good. Okay. So I think I'll start. I have few of the usuals coming in. Thank you, Govindada. So it's a pleasure to actually um, welcome all of you for this edition of the Wednesday Colloquium. And we have one of our own students returning back to give a colloquium. Professor Prerna Sharma, right now in Indian Institute of Science, Bangalore. She actually graduated, did a PhD with Professor Shankar Ghosh in condensed matter physics department. And this was in the period of 2005 to 2011. And it's absolutely a pleasure, Prerna, to host you for this colloquium. Just for everybody's sake, I'll just read the short bio data. It's important that you recognize how she evolved. So, Prerna actually did her bachelor's in physics from St. Stephen's. And although she wanted to do chemistry, and that's what I heard today, but she was forced to do physics because of family traditions, and she forced herself to love physics in the second year of St. Stephen's, her bachelor's degree, and then she got a chance to come to TIFR through the entrance exam and the interview as a INT PhD student. And at the age of 17, she pretty much entered here. And sorry, at the age of 20, she entered TIFR. And by 25, 26, she finished her PhD. This is absolutely sort of astonishing that she joined as a faculty at Indian Institute of Science after 3 years of a postdoc at Brandeis at the age of 28. Making her one of the youngest hires at IISc actually in the recent times. So Prerna's interest is in soft matter from her education and sort of the research education at TIFR, and her continued interest in going into biological systems, biological membranes. She has her research group is actually looking at these colloidal membranes and how they fold into complex topologies. That's part of the work, but she's also doing a lot of imaging work to look at these, tracking these geometries. Because of her interest in biology, and she actually applied for the Wellcome Trust DBT Alliance Fellowship, which she won as an intermediate fellow in 2016. And that enabled her to look at some of these exciting dynamics of membranes, colloidal membranes, using microscopy. So without further ado, Prerna, welcome back to your own place.
Thank you.
And we look forward to your talk.
Thank you, Jyotishman, for the kind introduction. So Wellcome Trust funded my research on ciliary beating, not on colloidal membranes, but so today's topic is colloidal membranes. My group works on ciliary beating and phototaxis and other biological systems as well. But today I'm going to focus on this subtopic. So the title of my talk is Folding of Colloidal Membranes into Complex Topologies. On the right, you are seeing 3D rendered image of confocal microscopy of these folded colloidal membranes. So as you can see, it's a very complex structure. It has many holes. and it has all this curvature associated with it. And I'll come to you how uh, we fold these sheets. So the outline of my talk is I'm going to talk to you about what are colloids, because my title has this keyword. What are membranes, and how do we combine to find something colloidal membranes? And then I'm going to finally come to how we fold colloidal membranes and why we should care about folding them, etc. So, so colloids are essentially dispersions of solid particles in a solvent. So for example, all these paints are essentially dyes or pigments in water, oil. All these creams are actually oil in water emulsion. So these are micro droplets of oil in water. And milk is fat droplets, protein droplets in water. So essentially, you're looking at some form of droplet or particle in some kind of suspension medium. And the key word is that these droplets or particles are micron in size, so that the thermal fluctuations are important, and these suspending particles would exhibit Brownian motion. And so why should we care about colloids? Apart from all the materials that we use in our daily life, starting from toothpaste and cosmetics and so on, there are these other applications that are also very fun. For example, bird wings have this kind of microstructure, and so the color that these bird wings have is actually, it's a structural color, in the sense that the light getting reflected off of this structure, the wavelength of the light is comparable to the structure in this microstructure in this bird wing. And so certain wavelengths get preferentially reflected off when you observe this color. Nowadays, there are these modern emulsions where instead of stabilizing oil and water through surfactants, you put in some colloidal particles which will go and decorate the interface. And then these emulsions are much more stable than standard surfactant-based emulsions. You can also have filtration as one of the key, applications, where essentially muddy water is nothing but a colloidal suspension, and you want to aggregate all these colloids to get filtered water. And so in that sense, colloids impact our daily life. And this is how they, this is how a chemist's colloid would look like. This is like, these are polystyrene beads that I'm going to play the movie now. Hopefully it plays, yeah. And they are jiggling in water through Brownian motion. This is a real-time movie, so I don't have the time that's going. Also, I think there is some, okay, that's, and so you can really, because of the micron size, you can use simple techniques like optical microscopy. They are slow. This is 10 to 100 milliseconds. And the reason colloids are physicists' darling is because you can do some fundamental science as well with them, in the sense that you can engineer the intercolloid potential or the interparticle potential to look like a hard sphere or Lennard-Jones like. And then the kind of physics that you would think about in atomic systems can be addressed here. And the advantage is, with the atomic systems, the length scales are very short, they're angstroms, and the time scales are in femtoseconds or lower. And here you can visualize and probe the same physics, but at a much larger length scale and much slower time scale. So there is some merit in looking at it. But before we do that, I'll tell you what are the sorts of interactions that we should worry about when we are working with colloids. One is van der Waals. Usually you think of it as a very weak force, and it scales as 1 to the power R6. But what happens is that when you are looking at van der Waals interactions between two micron size particles, you have to sum up all the contributions between the atoms lying on the surface. And when you do that, then this energy becomes very large. The attractive force is very large, and therefore this is a key driver of colloidal aggregation. So if there is no stabilizing force, there is no repulsive force, then they just flock together, and this is a colloidal flock that you can image under the microscope. So to stay, yes.
Density is the density is low enough so that the particle description is more appropriate than a hydrodynamical description.
Right. I mean, there are certain contexts where hydrodynamic description, the fact that they're suspended in water and there is, a flow around these particles becomes important. But when you have dense suspensions, then you stop worrying about these hydrodynamic modes of dissipation. So, so this analogy between atoms and colloids works best in dense suspensions vis-a-vis, free-flowing suspensions. Yes.
Thank you.
The fall is not 1 over r to the power 6. So for two, if you have two large plates suspended in water, then it's 1 over h square, because you sum up over all these contributions and then the scaling changes. Yes.
H is what?
H is the separation between two particles. Yeah. So, so you have to stabilize colloids, and you stabilize colloids by having surface charges. And so, so basically, electrostatic repulsion is what stabilizes colloids. And here, what I'm trying to say is that if you just think about a pair of electrons suspended in vacuum, then it's about 1 kT. And here I have large particles, so I have large number of surface charges. So typically, you have some kind of surface group that when you just suspend them in water, there is dissociation, and then you have a counter ion in the solvent and ion sitting on the surface. So think of it like sodium chloride. Chlorine ions will go into the water and sodium ions are sitting on the surface of the particle. So when you have something like this, then you have a larger amount of charges and you have the dielectric constant of the solvent. And then this can become hundreds of kT. But again, because of the counter ions in the suspension, it gets screened out. And so you have Debye screening with a screening length of about 10 nanometers. So you have a, exponentially decaying 1 over r times exponentially decaying potential between colloidal particles. Another way to, so electrostatic stabilization works when you have colloids in water. But when you have colloids in oil, then you don't have dissociation of ions. So how do you stabilize colloids in oil? And the way you do that is by adding a polymer brush. So then you get what is called entropic repulsion, in the sense that the suspending oil is a good solvent for the polymer, so the chains are all stretched out. Now, if you bring two hairy colloids close to each other, then the chains get entangled, and that reduces the entropy of the polymers, and that's that costs energy, and so that gives you an effective repulsion due to the polymer brush. If the polymer, this is true when the polymers energy with the suspending solvent is negative. So now in the dense suspensions, there has been a lot of work by the soft matter community and looking at phenomena that are theoretically predicted, in the sense what happens when you melt crystals. So there is something called Lindemann parameter, which is a measure of how much the atom is jiggling about its mean position, and that parameter sort of blows up as you get closer to the melting transition, and you can visualize and measure these things and test these predictions in colloidal systems. Similarly, in glasses, there is this idea that atoms, so glasses are essentially disordered materials which have very large relaxation times, and the idea is that the atoms in the glasses relax through this kind of cage hopping mechanism where they tend to jiggle around in a cage for some time before hopping, making a hop to another area of the material and then get caged again. And all of those could also be visualized very nicely in colloidal systems. And then the last fundamental science viewpoint is that here you can also look at gelation. So hopefully the video plays, and you can visualize gelation in real time and look at the structure evolution both in space and time with high resolution. So, so all I'm trying to say is that colloids are important both from a technology point of view, and they're important from fundamental science of point of view, where you can think of it as giant atoms in the sense whatever you want to learn about atomic systems can be easily probed here. Now I'm going to shift gears and take you to the world of membranes. So membranes are another class of soft materials, and our survival exists on having these membranes work, right? And so the particular kind of membranes I'm interested in are cell membranes or lipid bilayers, and they are made up of these molecules which have a hydrophilic head and a hydrophobic tail. And so when you put such molecules in water, they're going to assemble into a bilayer where they can shield the hydrophobic tails from water, and the hydrophilic heads are exposed to water. And so this is an overall energy minimizing configuration. And this is the building block of our cell membrane. So here I've just drawn one component lipid bilayer, but our cell membranes are of course much more complex. They have hundreds of different types of lipids and embedded proteins. And proteins and this protein lipid assembly is what makes this material amazing, and it gives us life, because it is what separates the contents of the cell from the inside and the outside. And these are, so lipids are nanometer size molecules. So the thickness of this sheet is few nanometers, and these are very soft sheets. Their bending rigidity is only 10 to 20 kpt. And composition of a cell membrane is of course very complex. So I'm trying to set the stage for colloidal membranes in the sense that again we have a system whose thickness and whose time scales are prohibitively difficult to probe. Of course, there are modern techniques to look at very short time scales, very small length scales, but there is some merit in trying to look for a good mimic of a cell membrane, quote unquote, a colloidal membrane. And there are in between a real membrane and colloidal membrane, there are in between model systems that are also useful and looked at by many other people. And I'll come to those systems as well, but I would first like to tell you the problem that that is a topic of this colloquium, which is membrane remodeling, in the sense that the membrane goes through these processes of endocytosis and exocytosis, or even in cell division, where there is large curvature generation. And then there are more complex systems like endoplasmic reticulum, where you can see that there is not only just a simple pinching of neck, but a large number of pores and holes with lots of curvature going on. So, and in biology, of course, curvature generation is driven by different kinds of proteins and cytoskeletal stresses and lipid arrangements and so on. But I would like to figure out simple mechanisms to fold membranes and simpler membranes to work with, because I'm a physicist. I can't. I would like to take the complexity out, just take a few component system so that I can get exact mechanisms out, which probably are relevant to these systems as well. So yeah, so since we are talking about curvature, and I'm going to be using some of these concepts. So this is a quick introduction to measuring curvature. So if you take a bottle of water like this, right? So it has it has two principal curvature. If you put your hand like this, you're bending your hand like this. So it's a convex curvature. But if you put your hand like this, it's a flat, right? So, so these are the two principal curvatures. Similarly, if you have any general surface, you will draw a normal vector, and then in that normal plane, you can identify, you can fit a circle and identify the radius of curvature in that plane. And so there are, so you will measure what is called mean curvature, which is the mean of the two principal curvatures, and Gaussian curvature, which is the product of the two Gaussian curvatures. Now, in these processes of fission and fusion of membrane, you will see the formation of neck. And necks typically have negative Gaussian curvature. So one side is concave and the other side is convex. And so that's negative Gaussian curvature surfaces. And so we're going to focus on generating negative Gaussian curvature surfaces. So now this is the first in-between model system that that is very popular in the community, which is a giant unilaminar vesicle. It's made out of lipid bilayer. So essentially, if you put lots of lipids in water and let them self-assemble, the bilayer would close up into a spherical object, and that's called vesicle. Its elasticity is given by a very simple Hamiltonian. So essentially, it has these two. So the first term is the bending term, which says that it costs energy to have a mean curvature associated with the surface. And then the second term is the energy cost for having a Gaussian curvature associated with the surface. And the last term is like a tension term. So now the interesting thing, so this Hamiltonian is actually a very generic Hamiltonian. It does not really care about the fact that you have this lipid bilayer or so on. I mean, your description is at a much more coarse grain level. You are just using the curvature of the surface and using some elastic moduli. So all you really care about is having a thin sheet, and then a thin sheet would have this kind of energetics associated with it. And
What is H and H naught?
so H is the mean curvature. H naught is if the surface has some mean, some spontaneous curvature associated with the membrane. K is the Gaussian curvature.
Last time is the pending.
Last time is over the boundary, yes, which is the surface tension integral. So the interesting part about this term, which is the Gaussian curvature. So usually people don't worry about the Gaussian curvature term, and that's because of the Gauss-Bonnet theorem, which says that the surface integral over the Gaussian curvature depends only on the topology and the boundary of the patch, meaning you can convert the surface integral into a line integral, and therefore for a vesicle it doesn't matter. And only if the vesicle undergoes some kind of topology change will this term matter. So basically the surface integral becomes a constant that depends on the topology of the system. So if the topology is not changing, then this is practically a constant in the energetics. And so that's the reason measuring Gaussian curvature modulus is very hard, because this term is kind of falling out of the energetics. And this is how the system looks like. So this is a vesicle that is fluctuating in water. And by analyzing these fluctuations, you can measure these elastic moduli, the bending modulus, as well as, so you can't measure Gaussian curvature modulus, but you can get the bending modulus. And you can also apply external forces. So here, this is a technique called micropipette aspiration, where you apply a suction pressure on this vesicle and it gets sucked in. So I'm not sure if the resolution is very good, but here this is before suction and this is after suction. You can see that there is a membrane that has gone into the micropipette tip, and so it's like a you have applied a certain force, and then you look at the deformation that the vesicle has gone through, and you extract the elastic moduli. So, but this system, as I mentioned, has its limitations. The closed 3D geometry prevents measurement of Gaussian modulus. If you want to observe dynamics of fission and fusion, here at high spatial resolution is a problem because the neck length becomes really tiny, and tuning the microscopic properties of GUVs is hard because then you have to be a very good chemist to change the microscopic properties of lipids, and then make the connection between microscopic and macroscopic. So you want to change the properties of your building block and then see how the macroscopic phase behavior changes, and that becomes challenging if you're working with lipid-based systems. And so I'm going to make a case that let's try to build a colloidal analog of membranes. And as I said, that the merit is that we will see similar physics at a different length scale. So just as we did it with colloids and atoms, can we do it with lipid bilayers? And I'm going to simplify this bilayer geometry into a monolayer geometry. And instead of lipids, I'm going to take rod-like colloids and make a two-dimensional geometry. So my Helfrich Hamiltonian, which describes the energetics of the bilayer, will stay the same, except these moduli will be much larger because now I have a very thick membrane. But I will have this advantage of being able to, because tuning the colloids is much easier than tuning the lipids. So I'll be able to change the properties of colloids and look at its effect on phase behavior, and I'll be able to probe it much more detailed.
Then there is a top and bottom layer. There will be correlations of this individual colloid between two rods. Now there are some correlation will be there.
So this is a bilayer of lipids, and I have a single layer of rods. So I don't have two rods. Okay, I'm not going to build a bilayer of rods.
I was thinking the top one layer, bottom is the another layer. So two surface you are looking at the properties in the surface.
Right. So I mean, there is a lot of what they call interleaflet interactions in lipid bilayers, which we are completely throwing out of the picture. But for the rods, I mean, just like lipid bilayers have a top and bottom surface, the rod membrane will also have some.
Top and bottom surface.
In your system.
Yes.
Biological membrane will be
Less correlated.
Okay, now I understood the question. I mean, I think for lipid systems, the correlation between the two leaflets is very hard to establish. So I'm not sure how, and both are like essentially, I mean, this picture is not really correct. I mean, this is schematic. So usually you think about lipids as like, kind of slightly entangled. Because it's entropically is favorable to have these hydrocarbon chains sort of entangled with each other than to sit like, two sheets that are apart. So I wouldn't really think of them as, I mean, I would think that actually the lipid bilayer is much more coupled because it's kind of like a hydrocarbon mesh that is, into each other. Yes, you have a question.
Will there be measurements of this kind of drifting of individual?
Thank you. Have there been measurements of how, maybe individual things drift by radio labeling or something?
Yes.
Across that might help understand what is the.
Yes, you can do single molecule imaging very nicely on lipid bilayers nowadays with all these high, Storm and STED kind of high resolution microscopy, but even standard fluorescence microscopy, you can do it. In terms of, I'm not aware of this exact, I'm not aware of the set of studies where people try to probe correlations between two leaflets. And again, the challenge here is because you have a nanometer thin sheets, when you have a fluorescence signal, it will be very hard to say whether it's coming from the top leaflet or from the bottom leaflet, unless you color them separately and ensure there is no interleaflet exchange. So I think it's a very challenging experiment to do it. And again, that makes the case for colloidal membranes because then you have very thick sheets to look at.
Are your rods directional?
No, they're not. Yeah. I will come to what my rods are because they are funky rods too. So the colloidal membrane should have these hallmark features of, so what are the features that I would like to retain? So lipid bilayers are, they're a very different kind of sheet in the sense that it has some long wavelength elasticity. You can measure bending modulus, but the lipids are free to diffuse. So it is a liquid-like sheet in terms of dynamics. So I would like to retain these two features, that it should be two-dimensional, it should have fluid-like dynamics in order, and it should have some elasticity associated with it, some long wavelength elasticity. And it should be simple enough to analyze theoretically and tune experimentally. So, so these are the features I would like to maintain. So the building block of the colloidal membranes, it's a virus. It's a bacteriophage. It's a virus that infects bacteria. It's FD virus or N13 virus. It's also popularly used in DNA origami if you're familiar with that. So the DNA that's used in DNA origami traditionally is from this virus. So it's a piece of DNA that's coated with proteins, and it's the same protein all along. So in that sense, also these rods are different in the sense I have a non-amphiphilic molecules. With lipids, I had this hydrophilic head and hydrophobic tail. There is no such head tail here. It's all just a uniform piece of rod. It has a length of 1 micron, diameter of 10 nanometers. So these are really sharp rods. And they are they're designed to be monodispersed because this is a templated assembly. It's a piece of DNA coated with protein. So as long as you maintain the DNA, you're going to get the same rod. And so you can get highly monodispersed suspensions. And it has very high surface charge. It is a chiral rod, and I'll come to that, what I mean by chirality. But right now, you can see this is, so this is a 3D EM structure of proteins on the rod, and you can see the proteins are helically wrapped, and that's what is giving the chirality to these rods, and I'll come to that as to how it manifests in the experiments. So what I'm going to do is, these rods are highly charged, so I want to bring them together, and the way I bring them together is using what is called depletion attraction. So where what I do is I add polymer coils into the suspension. So simplistically, you can just think that you're adding polymers, so you're applying an osmotic pressure to bring the rods together. But then you can question, why would I bring rods in a very specific manner of aligned way? And the way to understand it is that each of this polymer coil is, so these red things are the rods. There is a gray shell around them, which is the shell that the polymers cannot access. So they cannot, because think of them as hard particles, so they cannot penetrate. So there is some zone in which the polymer cannot enter. So now if I bring two rods aligned along their long axis, then these two gray zones will overlap. So there is some free volume that's available for the polymers to explore. And since the number of polymers is way more than the number of rods, the system maximizes entropy by bringing the rods together. Yes.
I still don't have a very good
Yes.
understanding of the rod material.
Yes.
What is the material for the rod?
It's you can think of it as proteins.
It's just proteins.
Proteins coated on a piece of DNA. So,
Okay.
yeah,
And
so it's a
they're
protein DNA
pretty
complex.
stable structures, you're saying,
Mhm.
right?
Yes, they're extremely stable. So this is a very tight packing of proteins. You cannot really, tell the DNA apart from proteins.
There is no way of proteins
Falling off.
disappearing or denaturing in that system, right?
Um,
Under the conditions that you work.
No, I mean, see, some denaturing will probably happen over time. These are purified viruses that you put them in some kind of buffer. Over months, some denaturing will happen, some proteins will fall off. But on a given rod, there are 2,700 copies of proteins. So typically, we don't worry about it. Yeah. Yes. Yes. Yes.
The outside part which you are saying they're overlapping,
Hmm.
how can they overlap? Because I mean, is it fiber kind or something, or
Outside part is not overlapping. I'm saying,
you have this
yeah, the
picture
yes, yes.
shows
So, okay, so what I was trying to say is the following. I didn't do a good job of explaining it. So, here is my rod, right? And here is my polymer coil. So, they can at best touch, right?
yes.
So, this is the center and this is the shell. Now, the center of mass of this colloid cannot enter here if I'm thinking of them as hard particles. So this is the zone from which the polymers are excluded. Okay, polymers cannot enter, and polymers would like to have as much space available to them as possible.
Yes, that's the thing.
So now if you bring two rods together, then their shells are going to overlap.
Yeah, this overlap part I didn't
Yes.
understand. How?
So
Maybe you can go ahead.
okay, I'll try one more time and then we can discuss it outside. So there is a shell like this for each of the rods, right? That part is clear. Now, when the rods are closer than a polymer diameter apart, then the shells will overlap. Yeah.
I'm saying that in the plate configuration, there's more excluded volume for the polymers.
Right.
Therefore, that's entropically not favorable for the polymers. On the
Yes.
right diagram, where
So
yeah,
here the shells will overlap, so there is more free volume for the polymers. Yeah.
so entropically more favorable.
Entropically more free. Yes.
So there's electric charge.
Yes.
So there will be strong repulsion.
Yeah, so we always put large amounts of salt to screen that out.
Yeah, that's the question I will have later. That's the remaining state. What are the size of this?
Size of this protein? Protein will be very small. It's 50 amino residue. So 50 acid. Each protein, but then there are like 2,000 copies of the protein. Yeah. It's P8 major coat protein. Yeah. So and so if you have large number of rods, they will come together and form this disc. And there are lots of polymers all around. Okay. And so at very high polymer concentrations, then these sheets themselves will stack up on top of each other through similar excluded volume interactions. But if you, but you know, there are these protrusion fluctuations. The rods can diffuse in and out of the plane, and you can visualize it. So here in this green is the rod, and you can see it pop in and out. So now at lower, so I think the important point is I can tune the strength of the interaction with the polymer concentration and the range of the interaction with the polymer size. So at higher polymer concentration, there is inter-disc depletion goes on, and that gives you stacking. At lower polymer concentration, where this attraction is weak, then there is this lot of protrusion fluctuation that leads to an effective separation out. So you end up getting larger colloidal membranes, which essentially just coalesce laterally instead of stacking up. And you get this beautiful large 20 micron two-dimensional sheet, which you can visualize face on and edge on. And you can measure the dynamics and fluctuation, and you can pull on them through optical tweezers. And so on a good day, your samples will look like this. So these are lots of sheets floating on the cover slip. The cover slip is coated with a polymer brush to suppress interactions with the substrate. And I've switched into fluorescence where 1 out of 10,000 rod is labeled. And the rods are pointing at us. So they appear as dots and they freely diffuse in the sheets. So it has fluid-like order and dynamics, and it has some long wavelength. Yeah, exactly. So you can watch the constituents diffuse. Yes. Hi. It is kinetically limited, but I mean, in the sense, see the discs kind of diffuse around through Brownian motion, then coalesce and become bigger. But when they become bigger and bigger, then they can't diffuse more and find other membranes to coalesce with. So yeah, so it's kinetically limited in that sense. Yeah.
I mean, I'm not sure if I'm able to express myself correctly, but in terms of your analogy to
Yes.
the lamellar vesicles and
Yes.
so forth, there's one thing inherent in those structures is that you tend to get uniform diameters more often than not. So in terms of you trying to make
Yeah.
that, so I'm wondering if you're thinking of all the forces associated with what goes into making a conventional biological
right,
vesicle as
right.
opposed to this control experiment.
Yeah, so I think strictly speaking, if you're trying to make GUVs, you always get some size distribution. You have to actually go to great lengths to get a monodisperse distribution. And here I'm not building vesicles, I'm building flat 2D sheets. And the size, again, you will have some size distribution that's just limited out of coalescence. Yeah. Yeah, so there's another factor that affects coalescence, which is chirality. So the rods don't want to be perfectly parallel with respect to each other, and they want to maintain a certain angle with respect to each other. There's a preferred angle. And how that affects the membrane. So these rods, if you were to make, if you did not add polymers and if you just concentrated them, they will make these liquid crystalline phases, where instead of getting a nematic, you get a cholesteric, where the rods would just like twist around and make a twisted nematic. And there are theories of, why chirality should exist and so on. I won't go into those details. It's related to the fact that you have proteins that are helically wrapped around the DNA. That is what is giving the microscopic chirality. The way it affects the membrane is, so this is a frustrated system in the sense that the depletion attraction from the polymers wants to maintain the rods perfectly parallel to each other, whereas there is this chiral interactions which want to twist it. So the way the system resolves it, it expels the chiral interactions to the edges, in the sense that at the edge you will see the rods are lying in plane. So you can do polarization microscopy. So schematically, this is what is happening. The rods are straight in the middle of the membrane. At the edges, they twist. And you can visualize that using polarization microscopy. So in the bulk, you have a symmetric whose director is perpendicular to the image plane. But in the edges, the director is lying in plane. So you get some signal in cross polarizers. And you can do what we call 3D polarization microscopy to assess the handedness. And the handedness depends on the microscopic chirality of the virus. And you can analyze this polarization, and there is an analogy to how superconductors expel magnetic field. Yes, yes.
Hi, Prerna. Sorry, I joined a little late. But are the rods uniformly hydrophobic?
I don't know about their hydrophobicity. These are proteins, that are.
I mean, they won't assemble in water unless they have hydrophobicity to some extent.
See, they would make liquid crystalline phases if you concentrate them enough.
Concentrate them hard enough, because we're talking about the depletion interaction. Because
even if you don't have depletion, even if you don't have polymers, and if you just keep on concentrating these rods,
they'll have some saturation concentration. I agree. But these wrapping sites,
yes,
that's a very interesting phenomena in even real biological membranes, especially slightly artificial biological membranes. There are beta wrappings that are used. So usually they use characters along the sort of length of the lipid to try to do something. They'll put proteins around, etc. So I'm wondering if that is some effect like that, or it is really due to chirality. So do you know that they're oriented in a certain manner? And if you take the D proteins, they'll be oriented in the opposite manner. Then it would be very believable that it's due to chirality.
Yes. So we can make these bulk lipid crystalline samples and we can assess the handedness of the chirality. We can also make mutants where we make an oppositely chiral virus. And then we can make membranes of the oppositely chiral virus and again check the handedness, and it's related to the macroscopic handedness. So in that sense, yeah. I mean, that's the beauty of the system, that we can really tune these things and check these questions. So, Jyotishman, when did we start? At 4:05 or?
You are right.
I have time.
Absolutely.
Okay. Yeah, no, but yeah. So, you can visualize the fluctuations of the membrane by, doing, this is a dark field imaging of the edge. And you can analyze, so essentially what you measure is the, quote unquote, the height of this, this interface. And then you Fourier decompose it into different modes and do a power spectrum of the modes. And you would find that the fluctuation spectrum will have a plateau value that's associated with the line tension. So for a droplet, we think about surface tension, a 3D droplet. Now this is a 2D droplet, so there is a line tension associated with it. And there is a finite bending modulus of the edge, which causes a fall off in the power spectrum of these height fluctuations. So from here, we can quantitatively extract the line tension of the membrane, which will become important in later parts. So far, all the experiments that I have done are with two-dimensional membranes. And I began my talk by saying I want to fold membranes into these neck-like geometries which have negative Gaussian curvature. Generating negative Gaussian curvature is far more challenging than generating positive Gaussian curvature, because then you just have to inflate something. But if you have to inflate in one direction and deflate in the other direction, it's non-trivial. So how do I introduce three-dimensionalness into the system? The way I do that is by introducing microscopic distortions, wherein I say I'll take a host membrane and I'll add shorter rods, because the length of the rod is under my control. So I'm going to take two viruses whose length difference is about 30%. They have the same chirality and similar other parameters. So the only change that I've done is the length, the chirality is the same. So what happens is that at low volume fractions of doping or at low osmotic pressures, the two kinds of rods are mixed. The red and the gray channels are fully mixed. At very high osmotic pressure, there is depletion, excluded volume interactions, which will drive phase separation. So the long rods on one side, the short rods on the other side, so that the polymer can have as much free volume as possible. So these are again still two-dimensional geometries. What was very surprising initially to us was that at intermediate depletion strength, you will start making these really strange geometries, which we later realized that these are saddles. So if you do a confocal of these sheets, they looked like this. And this is schematically what you are looking at here. And this is a 3D confocal data that is rendered to show that it's saddle-like in geometry. So this kind of video poses many questions as to, what will happen when saddles coalesce with other saddles? What kind of complex structures will I get? Why is the flat geometry becoming unstable? And are these saddles minimal surfaces, or, how do you relax these curved geometries into flat and things like that? So, and how does chirality affect all of this? So,
so just one quick question.
Yes.
So in the saddles, you don't have phase separation of the short rods and the long rods.
Yes, the two kinds of rods are fully mixed within the saddles. Yes, and that's important for generating these curved sheets. Yeah. Thanks. So I'm now going to analyze this a little bit more before I show you the complexity. So I have this confocal image of the saddle. I generate mid surfaces and analyze their curvatures. So the mean curvature and the Gaussian curvature. So what you can see is the mean curvature measurement is very noisy, but it's mostly hovering around 0. Whereas the Gaussian curvature is negative, as you would expect out of saggy. And what we did was we fitted what are called NA surfaces to these geometries to build some kind of simple theoretical model, basically be able to theoretically describe the shape that we have at hand. And the reason you would like to go from a flat sheet to a curved sheet is through this equation you can see. So your Gaussian, I mean, your energetics has the Gaussian modulus times the Gaussian curvature term and edge term, edge tension, okay, or the line tension. So for these systems, the Gaussian modulus is positive. I know that from other experiments, but from here also you can see. And so you can lower the energy by having negative Gaussian curvature, because then, but when you generate a negative Gaussian curvature, your edge length goes up. So there is a penalty to curve the sheet into negative Gaussian curvature. So therefore, only when the Gaussian modulus, the prefactor that sits here, is large enough that you will see this transition. If the prefactor is small, then the edge tension would force the sheet to be flat. So it's a competition between edge tension and Gaussian modulus. Okay, so theoretically, this is the full Hamiltonian for these membranes. It has the mean curve, the bending modulus times the mean curvature squared, the Gaussian modulus times the Gaussian curvature, the edge tension. Sorry, the edge tension. This is the main surface tension, and then these are the edge terms: the edge tension, the edge bending rigidity, and there is a geodesic torsion associated with this chiral edge. And we know most of the parameters here in this equation from previous experiments and from these sorts of height fluctuation experiments that we did. And so all you do is so R versus phi, the dots are the experimental data, which is essentially we took the experimental data, fitted NA per surface, and got R versus phi for the structure that we had. Then we solved, then we have this Helfrich Hamiltonian kind of energy, whose variation will give you a boundary condition for the edge. So this is a liquid-like sheet, so there is no shear force at the edge. So that gives you a boundary condition. You solve that. And theoretically, this is the kind of best fit you can get, and you get a Gaussian modulus as the only fit parameter, and that's about 1000 kT. Whereas the Gaussian modulus of a single component membrane is estimated to be about 200 kT. So I'm not showing you these experiments. This is another whole set of study that we had done earlier. But the point is that when we dope with shorter rods, our effective Gaussian modulus was very high. And that's what was driving the saddle formation. And so you can, so this is the theoretical phase diagram of the order of saddle versus the size of the membrane. And you can plug this into your energy equation and ask whether the energy of the saddle is lower than that of a flat membrane. And M is the order of the saddle that had lower energy than that of the flat disk. So the red points are the one which had the lowest energy compared to the flat disk. So experimentally, we found all these higher order saddles. So I had only shown you a simple saddle, but you can have all these really beautiful structures where you get these multiple minima, maxima going all around. So it's like a flower petal that is forming. And what we noticed is that these are, yes, these are my experimental data. I mean, many people confuse my data with simulation. So, so this is my confocal data of self-assembled higher order saddles. And what we noticed is that, so the same scale bar for all of them. And we noticed that higher order saddles required had larger area associated with them, which is what the theoretical prediction was also there. So we plotted M versus R naught for the experimental data, and so there is some, I won't call it a match, but whatever trend that the theory predicted is seen in the experiments. Yes. Yes. Right.
So I can understand how that kappa bar, which is the Gaussian curvature modulus, why that should increase as the relative number of shorter rods increases.
Right.
But how about the gamma? It doesn't have any effect on gamma. So you're saying that it just wins.
Gamma, the changes in gamma are much more moderate because gamma we can measure very accurately. We can do these fluctuation of the edges measurement, and that change is much more moderate than the changes in Gaussian modulus.
Nice.
Yes.
So one question. So don't you see something like which spirals on itself like a donut, but which is cut? So it will also have two surfaces.
I didn't catch your question.
So like,
a bit louder.
So do you have something which wraps around itself, like?
Yes. I will show you how things wrap. Yeah.
Oh.
Yeah. So, yeah. Yes.
You were doing this from the chapter
Yes.
But in principle, do you have accuracies to get distributions and more details of this? Or it's not possible within your experiment?
See, we did power spectrum for the fluctuations of the edge, but in principle, I mean, what other higher order quantities are you interested in?
Say 4 to the power 4 to the power. In principle, the full distribution, if you have all the moments.
Sure. Yeah, there are practical resolutions on spatial resolution and
so that's why I was asking whether it's possible or
I mean,
like fourth power or sixth power.
maybe fourth power I can't do. Yeah, I should be honest about it. I'm trying to sell colloids. We can do everything, but there are ultimately some limits to what colloids can do for you. So,
Thank you.
yeah. So going back to your question, what happens? Can saddles wrap on themselves and so on? So here is a DIC movie of how two saddles will coalesce. So this is a saddle, this is a saddle, it will coalesce, and it's going to do really something fun. It's going to become an unduloid or a catenoid. So and then these things can then further coalesce to make trinoid. And I'll show you the confocal images to convey to you what you just saw. So this is the DIC snapshot where you see two saddles which sort of come off the edges, like somewhere they merge somewhere in the middle of the two saddles. And then there is some kind of rearrangement that leads to an unduloid. In the confocal, you can see it much more carefully. It's actually not confocal, it's fluorescence which has been deconvolved to generate these stacks. But you take two saddles, fuse them somewhere in the middle, and then there is a nucleation of a pore that sort of opens up and grows, and you get a folded sheet. So this in my this is, I feel, first time we can watch a pore nucleate in great detail, and I'll show you how pores can close as well in the next few slides. Yeah.
Use some defect or something to have a folding at a certain point.
You would introduce defects if you merge at the boundaries, but if you merge somewhere in the middle, I don't really foresee any topological defects appearing. Yes, but defects usually appear if if the two edges sort of coalesce. Yeah.
Or
I'll show you some level of manipulation. So and so here are all these structures that formed in our samples. Okay, so I'll play, sorry, this video, how can I play? Okay, the video is not playing, fine, no problem. But these are, you can see this is an unduloid, trinoid, and all kinds of structures. And if you let them grow, you can really form gyroid-like structures. And so you can, so here here is a cross section of the video I just played. So many cross sections essentially.
Just let it happen for longer time.
Yeah, you just let it coalesce over time. So all these are actually intermediates. They will eventually coalesce into something very complex like this. And so you get these gyroid-like structures. So remember I showed you in the beginning that there is an endoplasmic reticulum which has this structure. So it's now with these colloidal building blocks, you can hope to, address the complexity and analyze the structure and dynamics of these systems. So this is just the beginning of trying to make complex folded objects at colloidal landscape. So usually gyroid-like or these triple bilayer kind of structures are common in lipids and surfactant systems. This is the first colloidal system where you can get the system spanning gyroid-like geometry. And so Kalu was asking whether if we have control on these shapes. So we can play games and games in the sense that these structures are sensitive to the osmotic pressure that's present due to these polymers. So I can use polymers whose osmotic pressure is temperature dependent. And then as a temperature as my tuning knob, I can introduce shape changes. So here the movie has already played actually. I'll play it again if I can, or just go back. It'll play again. So I had a flat sheet and then I've changed the temperature and the sheet will start to bend from the edges and eventually make a saddle with 3 orders, I think. Yeah, so there is some kind of pinching that happens and that leads to that. You can watch, you can do 3D imaging and you can also form helicoids, which are like a saddle that you kind of stretch. And right, so now I'm going to reverse it. So you're going to watch it go back to a flat sheet, right? And so these are really stimuli responsive sheets now where we can follow the dynamics.
Lowering the temperature.
Yes. Back to room temperature and right. There we are. And then the most beautiful in my opinion is this one where we had an unduloid which went back to a flat sheet when we changed the temperature and what you can see how it does it. It shrinks the hole at the top and then sort of goes and closes it. So, but this is irreversible. If we go back to this temperature, we're not going to fold it. We'll end up with a saddle, but we won't end up with an unduloid. So, yeah, and so this is the last slide where I want to motivate. Yes, Maitri, you had a question.
Can you can't make a biconcave disc.
Biconcave. No, I can't make a biconcave. I can only make it, one side concave, one side convex. So it's a saddle geometry. Yeah, I can't do RBC yet, if that's what you are hinting at. Okay. Maybe if I put a, yes.
One question. So the fact that you could not reversibly go back, does it mean you just got stuck in some, metastable state during your dynamics, which if you kept it long enough would actually go back to flat?
No, I think, so as I said, it won't go back to unduloid, but it will go back to saddles.
It will go back to saddles.
Yeah, so
are the unduloids like kind of
intermediates?
Stable. They're intermediate.
Yeah, they're intermediates. They will coalesce with other things and make a full system spanning gyroid, right? So
I see. Okay.
Yes, 5 minutes. Okay, last slide. Yeah, I wanted to motivate why the Gaussian modulus would go up when you dope with shorter rods. And so basically this is a video, hopefully it will play. No, it did not play. Okay, that's a pity. Maybe I'll skip the pointer and then it will work. How do I skip the pointer? I did. No, that's worse. Okay. Okay.
Oh, yes, yeah.
Okay, I'll click it. Yeah. So, yeah. So you can see that I am thickening up the saddle here, and you can see that the area away from the mid surface goes down. So the saddles are sort of compressed at the top and the bottom. Now, when you have only long rods or only short rods, then the rods have to tend to do something like this. And that's costs a lot of energy. But if I have short rods doped, then the rods can tilt and accommodate this compression. And therefore, the Gaussian modulus goes up when you dope with shorter rods. So this is a qualitative explanation. Quantitatively, you can see through the energetics. So my conclusion is that colloidal membranes are useful mimics of cell membranes, and we have demonstrated topological shaping of membranes through control of their elasticity, and we can observe real-time nucleation and healing of pores, which is a key phenomena in fission and fusion of cell membranes. And theoretical analysis suggests that the stability is controlled by the Gaussian modulus. So, thank you.
Thank you, Prerna. That was
Fantastic. The colloquium is open for more questions. Yes. Shudipto.
Really beautiful shapes, very nice data. Thank you very much.
Thank you.
But if you need to talk about cell membranes, the very basic first order thing that you're missing is the polarity of the lipids.
Yes.
So I was wondering if you could add something to the heads and make at least that first order connection to real cell membranes, because you're talking about pore formation and disappearance of pores. There, the reorientation of the head group, which is hydrophilic, is the most complex phenomenon. And it's beautiful, but it's essentially missing in your physics. Except I was thinking, if you're thinking it's a long rod, but still at the top, the way these things wrap, your top of the DNA must be exposed. And that's a very negatively charged thing.
Yeah.
So perhaps there is a little bit of a contribution where the tops are different from the sides.
Sure.
But in a length scale of 3 microns, whether that matters energetically is anybody's guess.
Length scale of 1 micron. So, I agree with you. I'm not claiming that this is the best, this is the most detailed mimic of cell membranes. I'm currently working on functionalizing the tips of the viruses, but it's going to be like a protein. So I'll display fibronectin or collagen on the tips of these rods, and then do some kind of interaction studies with beads or some other so it's like how would a membrane wrap around a complementary protein and things like that. Those studies will become possible. This exact hydrophobicity match, I don't think this is the system to look for. You could kind of wink it and say that this excluded volume interaction or depletion interaction is like effective hydrophobicity. I'm expelling water, so I'm expelling polymer, who cares? I'm expelling something. So in that sense, it may be relevant, but yeah, I mean, of course, there are, I mean, I would love to have some kind of cytoskeleton beneath these membranes and, have active membranes and whatnot. So my wish list is very long, but my means to catch up with them are still ongoing. Yeah.
I have a question.
Yes.
So it's regards to something that Shudipto was asking also.
Right.
These rods must have their own fluctuations with the protein structure.
Yes.
And I don't fully appreciate how these are very hard rods as you portray them.
Yes.
So is it possible that you can have a sort of protein interactions which are non-uniform across the rods? And or you have salts or maybe anions or cations in between, which will be critical to control. Even when you have these short segments, shorter segments doping in the larger segments. So do you have some sense of the molecular nature of the interactions?
Okay. So see, the thing is, I draw these schematics with the rigid rods. They're actually semi-flexible. They have some finite persistence length. In that sense, there is always some fluctuation at the rod length level that is going on. Of course, there is depletion which sort of penalizes this. You would want them to be sort of straight and have maximum overlap, etc. And then we can tune the rigidity to some extent. But how these fluctuations at nanometer, I expect these fluctuations to be at tens of nanometers. How that feeds into at the micron scale?
So for example, if
Yes.
I ask a question.
Yes.
Change the protein.
Yes.
Put another protein.
Yes.
Will it still have the same behavior of giving you a saddle point at certain concentration
Yeah, I mean, I can make
of polymer?
mutations in these proteins
Okay.
and I can still get
Okay.
samples.
Okay.
Yes.
Okay.
That much I can do. I can't change it fully because, that's ultimately.
So is this
provided.
very special system that you think, or we can do this in other systems too with similar kinds of ideas of a rod and not a DNA, but
Yeah.
um,
See,
the protein wrapped around
we have replicated the system with DNA origami rods also.
Okay.
6
Okay.
helix bundles, 8 helix bundles, you can get these. So in that sense, it's a generic system.
Generic system.
But you can't do this with silver nanorods or gold nanorods
right.
because they're heavy. They will, fall, and then you can't get them monodisperse. Here, the most of the phenomena relies on monodispersity.
Sure.
If that falls off, then you don't get liquid crystalline phases, and then
Sure.
it's all just goes down the drain. Yeah.
Thank you, Prerna. Any other questions?
Thing got clear that Pringles, this.
Yes.
Now I understood that the shape comes because of some particular temperature applied.
In oil.
That is actually non-uniform stresses that are generated in that's a separate. That's not self-assembled.
I think the team wants some chips right now.
Sure. We have some Pringles.
Okay. So thank you, Prerna. It's so much fun to listen to you after you left and you come back. So have a big round of applause.
Yeah, it was a great honor to be here, and I did not acknowledge my group, so I will acknowledge my funding and my group as well. Yeah, thank you. Thank you so much.
Thank you. Thank you very much. Thank you. And let's join Prerna for some snacks inside the West Canteen. So thank you.